Hello those students and welcome to your chemistry lesson. Today we'll be still looking at the topic the atom, but in today's lesson we'll be looking at other subtopics. These are the electronic configuration and isotopes. So let's begin the lesson with knowing what an electronic configuration is. Well, if you can analyze with me, you can see that in the word electronic, there's the word electron. And you also agree with me that to configure can mean to set up, right? So simply an electronic configuration is simply how the electrons are arranged or set up in the shells of an atom. Now, if you remember, we looked at the structure of an atom, right? And you can remember this picture I've just showed you right now. These rings are the shells of an atom. So under this subtopic, in this lesson, we'll be looking at how we can formulate and draw such a structure. Now, these shells, as you can see, have got levels, we can say. So this is the first energy level or the first shell. This is the second energy level or the second shell. And this is the third energy level or third shell. They are sometimes symbolized by letters. The first shell is symbolized as K, L is for the second, M is for the third, and N is for the fourth shell. Now, there's an important principle you should always remember when we're talking about electronic configuration. This is no other than the maximum number of electrons that can be found in each of these shells. Well, there's a formula that is used to represent this phenomenon. It's simply 2 multiplied by n squared. So to find the maximum number of electrons in any energy level or shell, you just simply square the shell number and multiply it by 2. So let's say we had the shell K. So we'll just get our shell number 1, square it, or simply multiply it by itself. So 1 by 1, which gives us 1, then multiply it by 2. And hence, the maximum number of electrons that can be filled up in the first shell are 2. With that said and done now, let's look at some rules that bind electronic configuration. There are 2 rules that bind electronic configuration, namely the duplet rule and the octet rule. I'm sure we've heard of the term duo, right? So when they say duo, they simply mean 2. We live in an information age, so you know that a phone that has got 2 SIMs is known as a dual SIM phone, right? So just want to remind you that whenever we see DU read as do, we're meaning 2. So even for this rule, it's based around the number 2. It simply states the maximum number of electrons in the first shell is 2. Now, if you know the names of polygons, you know that the number of a polygon with 8 sides is an octagon, right? The name of a polygon with 8 sides is 8 octagon. So simply this prefix oct means 8. And so this rule is also based around the number 8. and it simply states that the maximum number of electrons in the last shell is 8. Now, if you analyze with me again, you'll see that these two rules are related. The duplet rule looks at the first shell while the octet at on the last shell. And so it's easy to remember these two rules. So the duplet rule focuses on the first shell, and because of its name coming with the prefix du, which is do, it involves the first shell having max number of 2. That also applies to the octet rule. However, for it involves the last shell, but still, because of its prefix oct, it involves the number 8. Enough of those rules. Now let's look at how we can form an electronic configuration. I'm sure you can remember that in the previous lesson we looked at nitrogen. When we looked at the nuclide representation, we had an example of nitrogen. Now, how can we form the electronic configuration of nitrogen? Well, we just simply look at the number of protons, having that the number of protons is equal to the number of electrons. And because of this fact, we can form an electronic configuration and draw one. So to form it, what we simply do is we start listing the order in which the electrons are drawn in. So we said in the first shell, the maximum can be what? 2 electrons. If you can remember, this rule is just the duplet rule. And so we'll fill our first shell with 2 electrons. And then now we said in the last shell, the maximum number of electrons is what? 8. Then, once again, we go back to our formula to find the maximum number of electrons in a shell. So, you must always remember that that maximum number of electrons is also bounded to the rules. In the second shell, the maximum number of electrons is 8, because if we say 2 squared multiplied by 2, the answer will be 8. Now, nitrogen only has 5 electrons left. Do we fill up the remaining? No, we don't do that. We simply write the 5 there. This is because it hasn't exceeded the octet rule. So this here is the electronic configuration for nitrogen. Now let's look at another electronic configuration. We'll be looking at calcium in this one. It's a bit tricky if you don't know how to form an electronic configuration. So, like we did for nitrogen, we see if the duplet rule can be satisfied. So yes, the first shell can be filled with maximum of 2. Then we go to the next. Can the next be filled? Of course, yes. If we subtract 2 from 20, we're left with 18 electrons. We can still subtract 18, 8, and still be left with some more electrons. And so we fill even the second shell to its fullest capacity. Now, at this point, we're left with 10 electrons. What do we do? Do we simply just add the 10 like we did for nitrogen? We just wrote down the remaining electrons? No, we don't do that. If you do that, I'm telling you, your answer will be totally wrong. This is because we have the octet rule, which says the maximum number of electrons in the last shell should be 8. You should also note that we can't put the number 18 here because the electrons that are left and are not 18. They are just simply 10. So we put our 8 there. Now, we're left with 2 electrons. What do we do to that 2? Well, we add it there. And that's the electronic configuration of calcium. You might be asking, well, the last shell here will have 2 electrons. Why don't we just put the 10 there? Well, another explanation for this can be because most of the elements found on the periodic table will always be bonded to something. They won't be found usually as calcium itself. So usually these 2 here, when we find elements in the atmosphere, won't be present because it will be used in the bonding. And so usually the last shell will be this one, the third one. But always remember that the maximum number will be 8 in the last shell due to the octet rule. And so this is why we have 2, 8, 8, 2 and not 2, 8, 10. The last shell can't have 10. Now, let's look at another electronic configuration. In this one, we want to find an element which can make it possible to fill the third shell with 18 electrons. So in the case of bromine or bromine, the pronunciation doesn't matter. Guys, this is chemistry and not English. So I just want you to remember that bromine is the 35th element on the periodic table. And because of this, its electronic configuration might have 18 in the third shell. So like we did for the others, we see if the duplet rule can be satisfied. Of course it can. So we're left with 33 electrons. Quickly we will write 8 there. And now we're left with how many electrons? 25. So in the third shell, we know the maximum is 18 electrons. Can we fill that 18 electrons and still be left with electrons? Of course, yes. 18 is less than 25, and so we'll include that 18. Now, after we subtract 18 from 25, we're left with how many electrons? 7. And this completely exhausts all the electrons of bromine. And so this is the electronic configuration of bromine or bromine. Now, we looked at forming them. How can we draw these electronic configurations? Earlier this lesson, you can remember that you saw that diagrammatic representation of the structure of an atom. Yes, so when drawing these electronic configurations, we'll be just simply doing that. But what we just add is those numbers. For nitrogen, you can remember that the electronic configuration that we formed was 2, 5. So we'll just insert those values into their shells. Also remember that the commas were dividing the shells, right? So the 2 was the first shell, and immediately we put the comma, we were simply saying the number coming after this comma will be in the second shell. And so that's what we do. Simple. We indicate the ring there, and then a cross and a cross. You can also see that the elemental symbol for nitrogen is put in the middle of the ring. This is very helpful so that whoever sees your electronic configuration will know the atom which you're trying to relate to. Then after this, we simply draw our second shell, which had 5. And that's the electronic configuration for nitrogen. So now, you can see that in my electronic configurations, my electrons are arranged in a neat way, right? Yeah. So it's very helpful to arrange them in such a way so that when anyone sees them, it will be easy for them to count the electrons. If these electrons in the second shell were scattered, it would be a bit time wasting, I may say, or difficult to count the number of electrons. So most people, most teachers would like to group these electrons in twos. Now we move on to our next electronic configuration to be drawn, which is calcium. We won't draw the one for bromine because of time. You can pause the video and draw it. After this, you'll be competent to draw electronic configurations, I'm sure. So we do the same for calcium. Now, its electronic configuration we formed was 2,8,8,2. And so we just fill those electrons in two shells and it will look like this. The first shell filled with the elemental symbol for calcium in the middle, then the second with 8, the third with 8, and the outermost with 2. So these are drawn electronic configurations for nitrogen and calcium. I'm sure this is clear. This is why it's important to know the first 20 elements by heart, because you waste a lot of time flipping pages, going to your periodic table, looking for an element, then getting their atomic number. So it's very essential to know the first 20 elements by heart. Now, in this lesson, we're also looking at isotopes. What is an isotope? Well, an isotope or isotopes are simply elements that have got the same atomic number but different atomic mass numbers. Now, sometimes this definition is difficult to understand, right? For some people, but it's self-explanatory. So I like defining isotopes in another way. Instead of saying atomic number, I say isotopes are elements whose atoms have the same proton number but different neutron numbers. With that definition, it's easy for anyone to know what really isotopes are. So isotopes will have the same number of protons, and because of this, they are the same elements. Remember we said elements on the periodic table are ordered according to their proton number, as no two elements have got the same what? Proton number. So immediately an element has got same proton numbers, meaning they are the same elements, but they are an isotope of that element. Meaning they will only have what? A different neutron number. And because the neutron number will be different, the atomic mass number will be affected. Now, there's a fact that you should always remember. This fact is very important because sometimes questions might be based on it. This fact is true because isotopes have got the same number of electrons, because protons and electrons are equivalent in an atom, and so their chemical properties are not different. Now, their physical properties are different because their mass numbers are different. So they will differ in things like the melting point, boiling point, and density. With that said and done, let's look at the common isotopes that you should remember in chemistry. The first isotopes we look at are the isotopes of hydrogen. Hydrogen has got three isotopes, namely protium, deuterium, and tritium. We'll start with protium. So protium is an isotope of hydrogen that has got one proton and no neutrons. So its nuclide representation looks like this. Its atomic mass number will be protons plus neutrons, but it has no neutrons, so it will be 1 plus 0, and hence giving us the atomic mass number of 1. While for deuterium, it's got 1 neutron, and so the atomic mass number will be 2. For tritium or tritium, whichever the pronunciation again, it's got 2 neutrons, and so it's got 3 as its atomic mass number. And so these are the 3 isotopes of hydrogen that you should know. The most common is protium, and this is why you see it indicated on the periodic table. When you look for the nuclear representation of hydrogen, you always find it as protium. Now we look at the other one isotope that you should know. This is no other than chlorine. Chlorine has got 2 isotopes, namely chlorine 35 and chlorine 37. Now, you might ask yourself, well, on the periodic table, chlorine's atomic mass number is 35.5. How did it arrive to that? Well, it was after some analysis, some math, which is just simple, that they arrived to the atomic mass of chlorine being 35.5. What they did is they used the mass spectrometer, which is able to measure the abundance of an isotope in the environment. So they found that chlorine 35 has the abundance of 75%, while chlorine 37 has got the abundance of 25%. And what did they do now to get the mass? They simply multiplied the atomic masses of each of these isotopes by their percentage. And so they found 26.25 for chlorine 35 and 9.25 for chlorine 37. And so they added these two to get 35.5. And they decided to use this mass that was found to get the atomic mass number of chlorine. So that's all for today's lesson under chemistry. Look out for another lesson that will be still under the topic of the atom.